Welcome to Chapter 6 of our book, Understanding Pharmacoepidemiology. This chapter kind of follow the Chapter 3, where the different designs used in pharmacoepidemiology were discussed. Here we're going to talk about methodological issues related to the design in pharmacoepidemiology, mainly issues of internal validity. What are the things that the researchers in pharmacoepidemiology should watch out for when they're running their studies, specifically so that the interpretations are valid interpretations. So, as we did with other chapters, we're going to follow the book for most of the material. In some instances, I'm just going to do a brief overview. For other topics, I will do a more focused, in-depth discussion. Namely, for confounding, I will have a special video for that. I will let you know when we get there. So anyway, so as an introduction, pharmacoepidemiology, as we said earlier, aims at evaluating the use and effect of drugs in post-marketing phase. For that, secondary databases, if you remember that we discussed it in chapter 4, large databases collected for administrative claim processing or maintaining medical records offer that opportunity much more than a controlled trial. I think this point we have seen it more than once, meaning that controlled trials are good. However, unfortunately, because they're controlled, they don't represent what happens in real life, and therefore it's quite advantageous to use secondary databases that actually gives you a window of what is happening in the real world post-marketing. وحكينا عنهم in the chapter 4. These data were not collected for the purpose of the research question, thus pose challenges caused by a number of bias with regard to the use of drugs and patient outcome. Yani, the minute you step uh, um, into the field of non-experimental observation, non-experimental, which means observational data, issues with the internal validity they have to be addressed. Okay, so thus to be able to collect evaluate the association between the exposure and outcome, the importance to mitigate the effect of these biases and confounders. Come in, here's another issue. Associations observed in a study sample can be evaluated for statistical significance to determine if the relation can be used as chance only. Mainly, what we're trying to say here, and I think you've heard me say this in previous lectures, you're working in a sample, you're not working in a population, and therefore you should to be able to extrapolate to the population. You have to check if the results are due to chance only, whether is it statistical significance, معناتها they really reflect a real association that exists in the population. So that's the idea. Okay. So association resulting from bias is due to systematic variation and can be removed using study design technique or statistical analysis, which we'll address it later on in this chapter. Confounding association are caused by third variables and can be addressed at design level of analysis, which leads us to true causal association. Yani the point we're trying to make, or the author is trying to make, is that whenever you're looking at a study, you have to consider three types of errors. The random error, which is something that you test for using statistical techniques, and therefore you look at the p-value and confidence interval to tell is a statistical significance or not. You have error due to bias, and therefore you have to think about the potential types of bias that exists. So لما حكينا على ال different designs, we talked about selection bias, information bias, misclassifications. These are biases, يعني errors that are systematic, that are done systematically in a study, and therefore you need to try to prevent them. وفي a third type of bias which is due to confounding. And though we're going to go over an example here of what is a confounding, I will have a specific video for that. And the author ends up saying that if you're able to eliminate these three errors, you can get to causation, which command takes us back to what is a causation and how we have to be very careful when we're doing any type of interpretation. Not to say causation because it's a very strong term. Rather, we talk about association, relationship, correlation. However, to talk about causation, you have to check the Bradfield-Hill criteria, and you have to think about the causal pies, among other things. So first, let's talk about confounding. Um, this is a typical example of what a confounding, or maybe a typical definition of a confounder. What is a confounder? If you think about an exposure that is related to the outcome, so عندكم هون an arrow that goes from the exposure to outcome, meaning that the exposure is leading to the outcome. You may have a confounder when you have a third variable that is associated to the exposure and associated to the outcome. So you see the double arrows here. Okay, now this third variable can be thought of as a confounder if it meets the three criteria. Criteria number one, it's related to the exposure. Criteria number two, it's related to the outcome. يمكن هون in the book he talks about the confounder being a risk factor to the outcome, therefore كمان it's a one directional arrow only, and it's not in the causal pathway. Not in the causal pathway, يعني not biologically or pathologically related to the exposure. يعني the example of for example, if you exercise, by exercising your muscle, you build up muscle, and therefore there is a better oxygen tenure in your blood, and therefore you have a better health outcome. So oxygen tenure in the blood is not in the causal path. It is in the causal pathway, and therefore it's not a confounder. Okay. So let's see what the slide says. Especially concerning for observational studies occur when the relationship between the exposure and treatment and outcome is affected by another variable. The confounder is a risk factor for the outcome of interest. The confounder is related to the exposure without being in the causal pathway of exposure and outcome. So this is exactly what I just mentioned. I think here you have an example. So the exposure is the second generation antipsychotic, مثلا risperidone versus olanzapine. We're comparing these two with regard to the lipid outcomes, and a potential confounder is age. So age is related to the exposure. Maybe elderly people tend to take one or the other medication, and obviously elderly people again have a different lipid profile than younger people, and therefore, and it's not part of the causal pathway. يعني مش لأنه someone takes risperidone they become older in age, and it's not like that. So here age is definitely not in the causal pathway. So here in this situation, age could be a confounder. هلا مش ضروري it is a confounder. It could be, and therefore we need to investigate using stratified analysis, which I will address in a different video. So age, older age may be a risk factor for elevated lipid levels, and at the same time may also affect exposure pattern. Participants from young age are more likely to be prescribed the risperidone because of its indication in the children. Okay, so I hope it's clear. Again, I think this is more كمان examples and explanations. Confounding by indication. So basically, you have a specific type of confounding, confounding by indication, which fits the things we talked about. So whether you think about it as a, by indication or not, it's the same concept. And so the definition is confounding by indication arises when a physician prescribes drugs keeping in mind certain characteristics of the patients. So here, مثلا, we have obesity is a risk factor for pancreatitis. Beta, a diabetic drug, causes modest weight loss. It may be that doctors were more likely to prescribe the medication to obese diabetics. Because these patients were already predisposed to pancreatitis, confounding by indication may have occurred. Okay, so هل يا ترى البيشنتس عم ياخد الميديكيشن والميديكيشن is leading to pancreatitis والobesity ما له علاقة, or is it that if a patient is obese they're more likely to be receiving the medication and therefore the obesity is what is leading to pancreatitis and not the medication itself? Okay, so it's still the way we think about confounding the same way, however it has to do with prescribing a medication. Another type كمان is confounding by concomitant drug use. The example is evaluating the effect of second generation antipsychotic on weight gain and the use of a weight loss drug. In this example, the use of the weight loss drug could mask the real association between the two generation antipsychotic and weight gain. يعني the idea is to keep is the things the way we define how confining works and whether you apply it in a concomitant drug utilization ولا prescription, it's still the same concept of confounding. You have a variable that is associated with the exposure, associated with the outcome. It's not in the causal pathway. It may influence the relationship between the exposure and the outcome. Again, I will have a separate video where I go over the confounding and the way to deal with it with examples, with stratified analysis and multivariate analysis. Which takes us to bias. So by definition, it's a systematic error rather than a random error. And systematically, you're making something wrong in your study, which is leading for a wrong conclusion. So systematic error when one study group is selected in a manner that consistently treated differently than the other. We have two major families of biases. If you ever learn about bias, the larger two families in selection bias or information bias. Not to say that there's nothing else. There's a lot of different biases, but the two major types of bias. Selection bias: participants who get selected are more or less likely to experience the outcome than those who are not selected. And here you have two types of selection bias, and a self-selection bias or a referral bias. I hope the idea is clear of how selection bias works. Manita, you're getting a specific group that is not everybody, and those that are selected, when you compare them to those that are not selected, they do vary with regard to their outcome, out to their exposure. So for selection bias, participants themselves, so had is self-selection bias, the first one, themselves decide to participate in or drop out of the study. It's a decision that may influence by the exposure. If you think about RCTs, I know we should not be mentioning RCTs, but anyway, if you think about RCTs, one of the things that is done is the flow diagram, where you're comparing what is happening to those that participated and those that received the treatment and those that received the placebo. And one of the things you look at when you're doing the flow diagram, whether it's an RCT, حتى لو كانت cohort, you're looking at who is dropping off the study, who is stopping the medication, and you compare the two arms and try to see if there is consistently like a certain group of certain people that are no longer taking the medication, and if you compare to the placebo, they would be different people. So whenever you're reading an RCT, one of the things that you should see in an RCT is something called the consort flow diagram, and in that flow diagram, you should be able to see they're selecting by going out of the study. So the example says, study using retrospective electronic health records when studying the effect of the second generation antipsychotics on weight gain. Those patients with weight gain may be more likely to contact clinic to report the weight gain, and thus come to be on the radar of the study much more than those who did not weight gain, and thus did not call the clinic, and thus were not part of the electronic health records. So, yani, all we're saying that if in this study, if your study is based on a secondary database health records that is electronically, who end up being more on these electronic health records? يلي عندهم الأوتكم more so than اللي ما عندهم outcome. So في some sort of self-selection. So they don't have to necessarily know that they're selecting themselves to be part of the study, but there is a behavior in them that puts them in يا إما in a secondary database يا إما in a primary database for analysis. Okay, so should be reduced by using appropriate statistical techniques. This is something that we'll address in a minute. Another type of selection bias, or the second type, is the referral bias. It may occur when a patient is referred to another provider or referred to laboratory tests because of an exposure to drug. Let's read the example to see if it makes sense. Patient taking a second generation antipsychotic and a history of high glucose level may be referred to the laboratory for glucose testing more frequently. And I think it's clear here, right? I mean, إذا ما عنده history of glucose, they might not be referred as much as those that اللي عندهم. Okay, so the referral is based on their history. And therefore, when you go to get, remember, you're going to get the data from the labs. And therefore, you have no control of who's report and who's referred and who's not. And therefore, by the time you get the data from the labs, there is some sort of referral bias that already occurred. And therefore, there is overstating association between the two generation antipsychotic and diabetes incidence. Said that this is what's going to end up happening. It's a very nice example. It's simple, it's straightforward. I hope it's clear. The second family of biases هن information bias. So it's an error in measuring either treatment or exposure variable, which kind of links to the concept of how good of a measurement tool you're using, which you have to think about um, the validity and the reliability of the measure. Or if you're diagnosing, you should think about the sensitivity and the specificity of the test that you're using to detect the presence or the absence of the outcome. One of the issues that occur when you're doing information bias is the misclassification. وحكينا عنها مطولا للmisclassification when we addressed that in the prospective design and the retrospective design. So I don't think we need to discuss it here more than we did in other questions, the other. Okay, so هذا كله حكينا in the others. كمان في differential misclassification و non-differential misclassification. So on, they're just saying that the type of misclassification that can occur is the recall bias and the detection bias. Um, I think I mentioned the recall bias when we talked about the case control design. This is basically when the cases, so that's on the second slide. So this is basically when the cases tend to recall better their exposure than the control because of their cases of being a case. For detection bias, so this time, كمان it kind of act like a recall bias, but it's not the patient themselves that are recalling their exposure. It's more that um, uh, looking out for the outcome in a higher up step of effort in the exposed versus the non-exposed. If you remember when I talked about the designs, قلت لكم any kind of designs, you need to look at ascertainment of exposure and ascertainment of outcomes. And in any kind of designs, you have to make sure that you're giving equal opportunity of both the groups in terms of ascertaining the exposure and the outcome. So in a cohort and prospective design, after you split them into exposed, non-exposed, you're looking for the outcome. You should give equal opportunity for detection of the outcome in both the group. With case control, you split them into being a case and a control and the outcome occur. You should give equal opportunity in looking at the exposure. So that's here. This is what happens if you do not give equal opportunity. If you look for the if for the outcome more stringently in the cases than in the exposed than the non-exposed, that would lead to a detection bias. So when exposed participants are followed more closely than the non-exposed. In the example, patients on second-generation antipsychotics may be followed more closely for elevated blood sugar, blood glucose, and thus more diagnosis of diabetes may be offered in exposed treatment group compared to non-exposed group. Um, this is typical that happens in any kind of situation where you have a clinician مثلا doing a diagnosis, and that's probably why, مش probably, definitely why double blinding is done in RCTs, when the technician reading the X-ray is not told if the patient is taking or not taking medication, so that we protect how well or how meticulous the X-ray technician is in reading the X-ray, and thus giving equal opportunity for both arms of the study. Okay, I think this is just a continuation of the example. The authors concluded that there was no conclusive evidence of clopidogrel PPI interaction. The authors compared the result with contrary studies and suggested that the other study did not adequately adjust for selection bias. The author also mentioned the possibility of confounding by indication. That is, I think, the case given in the book. Anyway, so this is a short review of the possible threats to internal validity. And these are the major examples in terms of selection bias or information bias. What can we do to address these biases? You can address the biases at two levels. Okay, so في عنا الديزاين level of your study وفي عنا الاناليسيس level. how you analyze the data. So at the design level, these are the different things you can do to reduce the impact or maybe prevent the occurrence of the bias, randomization, restriction, blinding, matching. These are very simple concepts. For on the analysis, you can do stratification, you can do multivariate modeling. So stratification or multivariate modeling, you're going to see them when I'm going to do the how confounding video. Propensity score is also a very interesting thing that is more and more done nowadays. Instrumental variable كمان I will address it. أما مثلا for inverse probability of treatment weighing, مش هحكي عنهم كتير بالتفاصيل, they kind of like be complicated. Sensitivity analysis, you've seen me talk about this in when I talked about the loss to follow up in the prospective designs. كيف عملنا sensitivity analysis, like how would it been if that's a sensitivity analysis. And I told you that it can be done for different reasons. And I mentioned that next semester in the pharmacoeconomics, you will do sensitivity analysis, or you look at sensitivity analysis for different purposes. But anyhow, sensitivity analysis is also one of the ways you can use, you can do to address bias at the analysis level. So randomization. So randomization, you probably know what is randomization. I'm sorry, let me go back one slide. So basically, we're talking about methodological ways to address bias at the design level and randomization. So randomization is you already know what randomization is. You've seen it in the experimental designs. في عندنا different types of randomization. Block randomization is one of the things that we talked about. Simple randomization, stratified randomization, cluster randomization. These are different ways of randomization. The purpose is still the same. You're trying to make the two groups equivalent with regard to baseline characteristics. وبيقولوا إنه advantage of randomization is that you equalize the two groups with regard to variables you know about and variables you do not know about. And therefore, when you're reading a clinical trial, table one usually is the placebo arm versus the treatment arm, and compared with regard to the baseline characteristics, i.e., they're showing you that these two arms are similar, and therefore the randomization worked, and therefore we don't have reasons to believe that there is an issue of bias in this RCT. Okay, I don't have anything here because you know all of this. The second thing you can do is restriction, and basically restriction is part of your inclusion exclusion criteria. So if you think that a variable could be a potential confounder, you restrict your study to a certain group of this variable. مثلا if we go back to the example of age مع risperidone and olanzapine, and the outcome being lipid, so you strict, بما أنه you're worried that age might be confounded, you restrict your study to participants of certain age. So you don't have a wide variety of age. معنا elder group, younger group, so maybe only elder group will be part of your study. If you're worried مثلا that gender might be a possible confounder, you restrict your study to only female مثلا. If you worry that having had lifestyle مثلا is a potential confounder, you can restrict your study to a certain kind of lifestyle. The obvious disadvantage of this technique is that when you're restricting, you're impacting external validity because you can no longer conclude beyond the sample, the restricted characteristics that you imposed on your study. The third type that is done كمان at the design is the blinding, and you're very familiar with that. So blinding is when you don't allow the patients to know what they're taking حتى ما يصير في information bias. في double blinding وفي triple blinding. So in a situation when patient or data collector is ignorant of the treatment assigned, this is the blinding. Double blinding is when both patients and data collector both are blinding. Only data collector is more like it depends on the situation. who's the data taker. Sometimes it's the physician, sometimes it's the person responsible for the follow-up, sometimes it's the technician reading the lab X-ray, sometimes, it depends on who that person is. Triple blinding, you add to the double blinding the data analyst. You do not let them know. So all they know is that they're comparing group A to group B, but they don't know who's group A and who's group B. حتى ما يصير في mining of the data أو مثلا some some special effort in their analysis to reach the findings that they want. The fourth type of interventions that can be, maybe I shouldn't say intervention. The fourth type of things that can be done at the design level is matching. So what you do is you match the two arms or participants in two arms with regard to certain characteristics. So لو إذا عم نعمل مثلا RCT, you match a patient that is a male in his 50s to a patient that is male in his 50s in the placebo arm. So you can typically مثلا it's matched on age and gender. You can also match with things like educational level, etc. So once you matched according to a certain variable, that variable can no longer be investigated as a risk factor for the outcome. Okay, because typically what you have done, you have made the two arms similar with regard to this variable. يعني you forced that the placebo arm لنقول في بقلبه 20% male 80% females, and the treatment arm كمان 20% 80%. You forced it because of the matching. Okay. So if expecting age to be a source of bias, then the researcher can decide to match the cases and control according to age, making the two groups comparable with regard to a certain variable. But then one can no longer look at that variable as a potential independent variable. هذا اللي كنت عم لكم إياه. And once you match, you can no longer investigate this variable. The disadvantage is that costly, it's time consuming, and also honestly, it's very hard to match more than two or three variables. كمان in matching في عنا شيء اسمه one to one matching. يعني for every person you match a person, حتى if you matched two or three or four. In here you should remember the case control, where we talked about the number of controls that can be up to four versus one case. If you remember that slide, we discussed it in the retrospective design. Is that you're matching one person to four controls, but every one of these four controls is matched specifically to that person, then it's still one-to-one matching. The other type of matching is frequency matching. So what you do is you say, okay, in my cases I have 50% men, 50% women. I want to make sure in the other group I have 50%, 50% without going to one-to-one. It's called a frequency. It makes it easier to do the matching this way. But still, matching has its disadvantage. وحنحكي على something that is actually done at the analysis level, where it allows you to do matching with much more than only two or three variables, which is the propensity score. Hello, we'll talk about it in a second. Okay, so then that takes us to the how do we address the bias at the level of the analysis, yani the data analysis. The first technique is stratified analysis. Basically, you're going to look at the association between the exposure and the outcome at different levels of the confounder. And you will see that I will do that when I'm going to do the video on confounder. So, for example, if you're worried that gender is a potential confounder, so you're looking at taking medications and having a certain side effect. So you look at the association between medication and side effects for men alone, and medication and side effects for women alone. That is called stratified analysis. You can do something more, Kamen, which I will address in the other video. You can also do something called multivariate analysis, and I will address that in the other variable. But basically, it's like if you think about it as a linear model. Let me bring this here. Okay, so if you're familiar with the linear model, if you remember from the years when you were doing align, you remember that align has the following form, which is y is equal to a times x plus b. Okay, I think this is the kind that this is how you probably are used to seeing the linear model, where y is, in for us, y is the outcome. Okay, it's the dependent variable. It's depending on x, and x is the exposure. Okay, and then there is a coefficient that links these two together, will be as being the intercept. Anywho, what I'm trying to say is that this same model, if you write it up so that you add to this model plus هقول let's say I'm gonna call this one A1, so I add an A2 times Z, where Z is a potential confounder. Okay, so just by adding the Z into this linear model, into the model, okay, just by adding this into the model, now the model طبعا the value of this is going to adjust to the presence of the Z. Okay, and what you have done is you have done something called a multivariate analysis, and what you actually have done is you have accounted for the presence of this third potential confounder, covariate, let's call it. So you've accounted in the model, and therefore the relationship between these, the x and the y, has been corrected for the presence of this covariate. Okay, طبعا I'm not going into the math of it, I'm just explaining it take at face value. You will see it in the other video with actual SPSS outputs. But what I'm trying to say is, once you add, the minute you add into this model a covariate, then the relationship that used to tie up the exposure to the outcome gets adjusted for the presence of this covariate, and therefore you have controlled, we say we have controlled for the presence of this covariate. And it could be one covariate or another one, a second one, the third one, a fourth one, a fifth one. You can add as many as you want. And by adding these every time, this over here, the measures of the relationship between your outcome and your exposure gets to be adjusted for the presence of these covariates, and therefore you're actually correcting for the presence of these covariates in what is called a multivariate analysis. So it's called a multivariate analysis because you're having not only one variable in your model, but another variable and another variable and another variable, and therefore you end up with a multivariate analysis. Basically, هكتبها هيك just so that for the fun. So you start off with a simple model where it's ax plus b, okay, and then a multivariate model will be equal مثلا ax plus, so هسميها هيدي a1 a2 just so to note that these are different. z مثلا is a different variable, plus لنقول a3 ولنقول مثلا r is a third variable, okay, okay, and that is the intercept is a phi intercept. So basically this is considered to be a multivariate model. Okay, so to control multiple confounders at the same time, we calculate parameter estimates that provide information on the contribution of each individual confounder to the occurrence of the outcome. We need to specify a model and use multiple regression techniques. يعني all you care about all of this is the multiple regression technique. معناتها we're using a model that allows for the presence of these multiple variables at once, and by the mere fact that they're present together in the model together, they're actually controlling for each other, and then your estimate is no longer impacted by the confounder. Advantage provides information on each confounder separately, and if we go back here, every confounder, the header confounder comes with its own measure of association. Okay, يعني مثل ما هيدي, so this is your exposure, and the A1 is the measure that associates X with Y, then A2 is the measure of association between the outcome and confounder number one, and A3 is the measure of association with the outcome and potential confounder number two. By the way, they do not have to be confounders. They could be multiple risk factors, and you're adding them up together in one model. كل وحدة منهم لهولي are risk factors, and every A is a measures of association for every one of these risk factors. Okay, so another thing that you can do is propensity score. Propensity score is a very versatile technique that can help you do something that looks like matching. However, you're matching for multiple variable at the same time. What you're trying to do is you're trying to mimic RCT. So you have, let's see. So you have two groups. Okay, maybe it's a cohort, or maybe it's a case control. Moham, you have two groups. Okay, so that's group one and this is group two, and you want to compare them, right? With regard to the outcome, but you're worried that the baseline characteristics of these two groups are different. Okay, so هذه عندها baseline characteristics وهذه عندها baseline characteristics, and you're worried that they're not equal with regard to each other. So one thing you can do is you can ask the computer to run an analysis where it's going to use these predictors. So you put everything together in one data, and you ask the computer to use these general, يعني نقول baseline characteristics كان gender, age, education, health insured, and whether they are sedentary ولا لا. Okay, so we're going to stop at these 5 variables. So what you do is you ask your computer to use these 5 variables to predict if the person belongs to group 1 or group 2. Okay, we're not predicting outcomes, we're predicting to which group they belong to. يعني لنقول كان group 1 or group 2 is whether or not they're taking drug 1 or drug 2. Okay, so we're looking at 2 drugs with regard to the occurrence of side effects. So in propensity score, you're ignoring side effects for now. You're using the baseline characteristics to predict which group they belong. Okay, and based on these baseline characteristics, every individual will get a probability of belonging to the group. Okay, so مثلا the first person is going to get a probability of 0.8, the second person is 0.4, etc. Okay, so these probability you can think about them as scores. They're called propensity scores. when a group 2 نفس الشيء مثلا حيكون عندنا 0.7 ل first person, 0.2 ل second person, 0.9 ل third person. Okay, so you end up with scores, propensity scores for group 1 and propensity scores for group 2. Then what you do is you're going to use these propensity score to match these two together. So بتقول okay, أنا عندي هذا الشخص عنده propensity score of 0.8. في حدا in that group that has a propensity score of 0.8. إذا طلع في حدا, so these two people will be matched. Okay, and let's say when you have somebody whose a propensity score is 0.2, you say, okay, this person is propensity score of 0.2. I'm gonna use that to match with this person. Okay, so you end up doing a matching based on propensity score. Well, propensity score itself is based on the baseline characteristics, and therefore you kind of have matched the two groups with regard to the baseline characteristics, but not each baseline characteristics by itself, rather by given a score that represents the baseline characteristics. Okay, so what that does, it makes the two group, by matching, it makes the two groups equivalent with regard to baseline characteristics. So it kind of like mimicking, in Chinik we say it mimics randomization. It's kind of like trying to do what randomization does, but with a different approach. Having said that, you should note that some of the participants might not end up being matched. Okay, so you lose them. So very often what happens, يكون عندك sample size of, let's say, 4,000 in every arm. After matching using propensity score, you may get down to 2300. It happens. It's perfectly normal. And I have an article that we'll look at it and we'll see how it works. So let's see how we described it here and see if it makes sense what I just explained. So the analysis is used in order to mimic the condition of RCT. Yes, any propensity score try to mimic randomization to make the two groups equivalent. It is used to balance the treatment to group on all the observed characteristics. مثل ما قلت لكم, we try to make the two groups equivalent with regard to the baseline characteristics. Using a logistic regression model, probabilities of being assigned to a treatment group are calculated in the observed characteristics. So that's what I'm saying. You use the certain program statistical technique to produce a probability and a propensity score for every individual that is predicting if they belong to group 1 or they belong to group 2. Okay, so every person will have a score ranging from 0 to 1, and then what you do is you try to match those that have this very high propensity scores, and you try to match them based on propensity score. So similar probability of propensity score are considered similar patients, and therefore we match them based on that. This method is used in pharmacoepidemiology and comparative effectiveness studies to control for selection bias. So that's the propensity score technique, and we have an article, we'll probably discuss it in class. Instrumental variable estimation. Kamen, it's one of the tricky things that is used in trying to control bias. And let's see. So, um, so instrument variable estimation, this method accounts for unobserved factor that may be affecting treatment assigned, unlike propensity score analysis. So we have an observed factor. Okay, it reduces the selection bias at analysis level. Look for an instrumental variable. So here's the core of the thing. You're going to look for a variable that should be correlated with the exposure, but should not be correlated with the outcome. Yani you should know that this variable makes no sense to be associated with the outcome, but you know it's associated with exposure. And then you run a regression, is then used to predict the treatment assignment for each patient using the instrument variable, the predicted value of the exposure, and then replaces the actual treatment variable, and the association between the predicted and the outcome is done. If an association exists, then it should be free of an observed bias. Yani, Anna, my understanding is the following. If you have an exposure, so let's say this is your exposure, and you have an outcome, okay? And you have this variable here, your instrumental variable, okay? You should know that this here makes no sense. This has nothing to do with the outcome, okay? But you know that this instrumental variable is related to your exposure. And therefore, when you look at the association and you find that there is an association between the instrumental and the outcome, it can only occur because of this relationship between the two, and therefore you conclude that that the relationship exists between the exposure and the outcome. However, since you're replacing the exposure by an instrumental, any factors that may bias this relationship is not biased, because you're not actually looking at the exposure, you're looking at the instrument. Let's see if this makes sense if we reread the head and we look at the example. So you look for an instrumental variable that should be correlated with the treatment. It should correlate to the exposure. You know that, but should not correlate with the outcome. Then you use an analysis to predict the treatment assignment for each patient using the instrument variable. Then the predicted value. So what we're going to do is you're going to use this instrumental variable to predict if a shakhs is exposed ولا لا. You use the predicted value of the exposure, then replace the actual treatment variable. So this predicted value of the exposure replaces the actual treatment, and the association between the predicted and outcome is done. It is non-existent. It should be okay. So what happened? Let me explain a little bit. So لكن اتفقنا إنه the instrumental variable should not be in principle related to the outcome, as I said. So عندنا exposure وعندنا outcome. Okay, and we worried that this relationship هون بين هول الاثنين is impacted by a lot of bias. Okay, so what you do is you pick a variable. the instrumental variable, which you know is related to the exposure, you know في relationship, and you know that there should be no relationship between these two. Okay? So by definition, this is not a confounder, صح? نحن قلنا for a confounder to be a confounder, it should be related to both. Okay? But what you're doing is you're trying to replace the exposed by the instrumental variable. Okay, you don't use it directly, use it as a predictor of this. So you use this to create another version of the exposure, but it's a predicted version. Okay, and then you look at the association between the predicted and the outcome. Now this relationship here is produced from these guys over there because you created this relationship using this over here, which is not directly related to the outcome, and therefore it's free from the impact of these potential biases. I hope it's clear. Let's look at the example. So researcher wish to estimate the causal effect of smoking on general health. So the exposure is smoking, with general health is outcome. Correlation between health and smoking does not imply that smoking causes poor health because other variable may affect both health and smoking. So نرجع our example. In this example اللي عم نحكي عنه هلا, this is smoking and this is health. So just because you saw a relationship here, it's not automatically that smoking is related to health because of the other things that may impact. Okay, هذا اللي عم نقوله هون. Okay, so not implied because other variable may affect both health and smoking, هذا اللي قلنا, or because health may affect smoking type. It is at best difficult and expensive to conduct control experimental on smoking status and the general population. يعني ما فينا نعمل control study. The researcher may attempt to estimate the causal effect of smoking on health from observational data by using the tax rate for tobacco product as an instrument for smoking. So what's going to happen is that they're going to use tax. We know tax is related to smoking, right? The more you smoke, the more you're paying tax. But paying tax does not make any sense to be related to your health status. Yani, the more or less you pay tax, you're going to have a better health. It doesn't make any sense. So we know that tax is not related to health, but we know that tax is related to smoking. Okay? Let's continue. Okay, the tax rate for tobacco product is reasonable choice for an instrument because the researcher assumed that can only be correlated with the health. So let me repeat that. The tax rate for tobacco product is a reasonable choice for an instrument because the researcher assumed it can only be correlated with health outcome through the effect on smoking. That's what we're saying. يعني ما معقول tax is causing the health outcome. It has to be through smoking. If the researcher finds tobacco taxes and state of health to be correlated, this may be viewed as evidence that smoking causes the change in the health. Okay? لكن as we said, إذا لقينا إنه tobacco taxes is related to the health, that could be just, it cannot be anything but due to smoking. And since you're investigating this relationship here, which is free of that sign here, of this, يعني those things that are impacting this cannot impact high. Okay, and therefore this association is free from these potential confounders. More specifically, the researcher can use tax rate to predict tobacco use. هذه بقى هون قلنا predict. Okay, so you're going to create a prediction of the tobacco use, and then this new predicted tobacco use is said to be free from bias because it was created solely from tax rate variable. The association between health and its new predicted tobacco use is checked, and if it's significant, it would be free from bias. Okay, so this is I hope it's clear now after we explained it. Now there is the inverse probability of treatment weight. I'm not going to address it. Sensitivity analysis, I kind of have gave you an idea, but let's read it anyway. Several assumptions are made to examine the association between a treatment and the outcome. A sensitivity analysis is conducted by systematically repeating the analysis of association between a treatment and an outcome and varying the assumption made each time. So that's the key term right there. You're making a certain assumption, and every time you're playing with this assumption. This is done in order to assess how sensitive the results obtained are to the variation in the model assumption and whether results are consistent across these variations. Consequently, sensitivity analysis is a way of checking the robustness of the association between an event and an outcome. One-way and multi-way analysis can be done. It can also show potential effect of unmeasured bias, such as confounding. This can only be performed if measures of the effect and prevalence of conflict is predicted in literature. All right, so I'm not sure about this point, and therefore I'm not going to spend a lot of time explaining it. How is sensitivity analysis performed? Um, Come in. I'm just gonna go over reading and with examples, and that's it. Okay, so it is otherwise known as the what if analysis. I think I mentioned that. Its executions follow the simple motto of change the model and observe its behavior. Therefore, any parameter that fits the frame of the study can be altered to see the effect on these variations. These parameters may be tested when switched one at a time or simultaneously. Simultaneous variation of variable across a reasonable range is a process called probabilistic sensitivity analysis. Let's look at the example. A study was done to evaluate elderly patients' medication adherence to their hypertensive medication. The outcome will adhere to medication. The analysis, medication procession ratio, was used to measure the outcome. It enabled researchers to classify patients respectively after the intervention as adherent or not adherent. So the key here, and we're going to classify the people as adherent ولا لا based على شو based على cut point of 0.8. Okay, so هذا medication possession ratio, it's a ratio, and you know a ratio varies between 0 to 1 to more than 1. So here they're saying if you had a score, a ratio of 0.8 and above, then you can be considered as adherent. طب هذه 0.8, how magical is this number? And I think that's what they're going to do. They're going to change the 0.8 and rerun the analysis and see what happens. So how would a sensitivity analysis be conducted in such a study? I think I just answered that question. One option would be to change to vary the ampere value at which researcher will classify patients as adherents to non-adherents. يعني بدل 0.8 بيستعملوا 0.9 and they rerun the analysis to see if there is an association between, I think it was elderly يعني, and medication adherence. Another option would be to use different methods for assessing adherence, such as PMC. So totally change the method where you're measuring your outcome, use a different one and see what you get. Another option would be to vary the cutoff of point of age for elderly. So what is the definition of elderly? Above 70, above 65, above 75. So you start changing these cut points, rerun the analysis and see what you get. Come in. Another thing that you can do at the analysis is the risk adjustment. So often observational study treatment groups are different in clinical and non-clinical characteristics, and I think we have mentioned that more than once. The issue of you have the two arms not being equivalent, that is a potential problem. And that's why we talked about propensity score من شوي. We wanted to make them equivalent. These differences may influence and confound the outcome. Therefore, it's important to remove the impact of these risk factors to arrive at the correct estimate of association between treatment and outcome. Yani the idea is you may have a lot of potential confounders. What can you do? The risk adjustment, the rationale for risk adjustment is to evaluate the outcomes by statistically controlling for group differences, but when comparing them. Simply put, if you understood لما كنت عم بشرح multivariate analysis model, and we start adding these into the model, and just by adding them, you're actually controlling for them. I think that's what the adjusted for risk. This is it, as simple as this. You're running a multivariable model. You're adding these possible risk factors or covariates or confounders. You're putting them in the model, and just by doing so, you control for their presence. So risk adjustment is used to calculate an unexpected outcome measure based on the risk factor considered and the relationship with the outcome. Okay, so here's the thing. Sometimes when sometimes the concept of how risk and how severe a patient is can be actually measured in one variable, and therefore you can actually use these measurement of the risk to control for. And there are different ways in the literature available for you to utilize these risk adjustment. مثلا يلي شغل بالأباتشي. I don't know if you ever heard of the Apache. Apache is also like a technique on for measuring how bad the patient situation is. So بدل ما أطلع على multi things, I do the Apache, and based on the Apache, I can have one variable that represents how bad the patient situation is. And it's a way of, instead of having multi variables to understand a concept اللي هو health situation of a patient, I create one score that would represent that, and by adjusting for that one score, I would be adjusting for everything else. So the main factor considered in risk adjustment in the treatment, the age, sex, the extent and severity of comorbidities, etc. So extent and severity of comorbidity is in red, I think, because it's one of the most important ones. وفي عندكم examples بعدين in the slides. I'm not gonna go over them about like the different ways you can adjust for them. So here you have adjustment for comorbidities, an example. Here's its risk adjustment based on the diagnostic base model. So في عندكم Charlson Comorbidity Index, the Ilks-Hauser Index, the adjusted clinical group. كلياتهم they're trying to do the same thing. They're trying to figure out how bad the situation of the patients. So I'm going to slide that explains the Charlson comorbidity, the Elix-Hauser index, the third one. كمان الأباتشي اللي حكيتكم عنه كمان is one of the techniques. And then you have risk factors that are used in the pharmacy more than in other sorry, more than other fields. So you have the chronic disease scores. ما حفوت فيهم، ما حفوت بتفاصيلهم. They're specific to those that work in certain fields, but the concept is the same. You're creating a score that is supposed to reflect on the patient's health condition. All right, so let's see if I have anything else. Let's look at the case study. Cardiovascular outcome and mortality in patients using clopidogrel with PPI after percutaneous coronary intervention of acute coronary syndrome. The FDA has issued a warning about the reduced efficacy of clopidogrel when used with PPI concomitantly. Studies were conducted to estimate the risk of reduced efficacy and increased adverse cardiovascular effects, MI, hospitalization, and deaths. The results among the 18,000 and something participants, MI development was 2.6% with PPI versus 2.1 without PPI. Regarding death, 1.5 للPPI, 0.9 without PPI. Underwent revascularization, 3.4 مع PPI, 3.1 without PPI. Rate ratio for the primary endpoint of MI or death was found to be 1.1 مع confidence interval, which is not repeated here, and therefore the conclusion, there was no conclusive evidence of clopidogrel PPI interaction. Here's another case study. A 3-year study was done to investigate the association of BDZ usage and the risk of injury following outpatient and inpatient data. The total of prescribed was 133,000 for 13,000 unique patients for the VA Medical Center. The variables that they looked at in the hospital discharge, marital status, etc., but they also looked at the Elix-Hauser comorbidity measures as a way to control for the risk adjustment of the condition of the patients. In conclusions, variables that were not found to be associated with an increased risk for injuries were dose, duration, discharge, various comorbidity, BMI. These findings showed that the effect of many combinations of risk factors may influence risk of an outcome such as accidental injury risk in this case study. The study provides a good example of diagnosis-based risk comorbidity adjustment in a pharmacoepidemiology study. Anywho, so that's conclude this lecture. We still have another lecture about confounding where we're going to talk about it in details in terms of stratified analysis and multivariate analysis. Thank you for your time.